Konnichiwa, my name is Bisqwit and today I'm going to show you an intuitive method of creating a software 3D renderer that can be used for simple games. Now before we begin, I do realize that your GPU probably has immense power that is specifically designed for this job and it makes no sense to not use it, but many people, myself included, are interested in how this all works, so let's go through it all manually. There are many ways to create 3D graphics. You could create it from tiny spheres, let's call them atoms. That's what the real world does, so it's the best solution, right? There's just one problem, you need gazillions of them. Many orders of magnitude more than is possible to handle on computer hardware still for a very long time. Instead of spheres, you could do data points and interpolate between them. This technique is called voxels and has a long history in computer graphics used by games such as Comanche. However, you need to restrict your world to certain shapes, such as a flat land or very large cubes, or you have just renamed the gazillions of atoms problem. That isn't to say that voxel graphics cannot look pretty. This footage is from an upcoming voxel graphics game called Cloudpunk. Ray tracing is another approach. This creates very realistic graphics and is barely doable with modern hardware. It involves calculating for each pixel the possible intersections and bounces between light sources and the ray representing the direction where light is collected for that pixel. It is still not the dominant method of graphics. What nearly every game and application actually uses is polygons. Polygons are flat, infinitely thin textured surfaces, which are often very small and can be combined to create the appearance of complex objects. Polygons do not have substance. Walls made of polygons do not have material. They are just paper-thin structures in vacuum. People made of polygons don't have material. They are just as hollow as the walls are. In fact, it is wrong to say they are paper-thin. They are infinitely thin. Just like a circle doesn't exist in the real world and the closest you can have is a cylinder or a torus, polygons do not exist in the real world. They are purely mathematical. Nonetheless, just like dabs of paint on a canvas, polygons are very useful for all sorts of visual presentations. But you need thousands or millions of them. For this reason it is important that they are as simple as possible. Follow the Unix principle. Do one thing and do it really well. Or in Bruce Lee's words, fear not the man who has practiced 10,000 kicks once. Fear the man who has practiced one kick 10,000 times. One way to reduce the complexity is to reduce the number of corners in the polygon. The simplest possible polygon is the triangle. It has just 3 corners. If you go any smaller, it is no longer a surface. A line has no surface. Triangles are simplest polygons. If you have 4 or more corners, you may need to worry about the polygon being non-convex or possibly self-intersecting. These concepts are simply impossible with a triangle. When you render triangles, you do not need to worry about these special cases because it is impossible for them to occur. And if you do need more complex polygons, you can always build them from triangles. The process of drawing a polygon is called rasterization. Raster is simply a fancy name for a grid like this, like a squared paper. The computer screen is also a raster. Imagine that each of these little squares represents a pixel on the screen. So what do you do when you have a triangle like this? You have to color those pixels which fall inside the triangle and ignore the rest. But how do you do that? You could approach it mathematically. Calculate the bounding box of the triangle and for every pixel inside the bounding box, test whether it is on the same side of every edge of the polygon. If every pixel is on the same side, then the pixel is inside the polygon and you may plot it. But how do you plot it? You may use the plane equation of the triangle together with the display geometry to convert the 2D coordinate into a 3D coordinate and then reverse the view rotation and translation in order to get a world 3D coordinate and use that 3D coordinate as an index to some texture and fetch the pixel from the texture at that point and plot it on the screen. You could do all this and it would work. While this would be extremely easy to parallelize, it would be very inefficient. So many mathematical operations for each pixel. What I am going to introduce is a very simple and intuitive scanline polygon rasterizer. Let's begin by analyzing the anatomy of triangles. Measuring the relationship between x and y coordinates of every corner, I have counted a total of 28 different triangle shapes. In 5 of them there is a horizontal line at the top, and in 5 of them there is a horizontal line at the bottom. In the other 14 there is a bend somewhere in the middle. In 7 of those the bend is on the left side, and in the other 7 the bend is on the right side. The bend is indicated in magenta color in this slide. However, the top and bottom cases are simply special cases of the middle 14. The top and bottom cases still have a bend, but the height of the bend is simply 0, so we can ignore those and concentrate on the remaining 14. These have 2 major categories, ones where the bend is on the left and ones where the bend is on the right. Within the groups of 7 triangles, the differences are where the corners are positioned in relation to the other corners. For example, in this triangle, the bottom corner is on the left side of the middle corner. In the next, the bottom corner is in the same column as the middle corner. Here the bottom corner is on the right side of the middle corner. Here it is in the same column as the top corner. Here it is on the right side. In the next one, the middle corner is in the same column as the top one. And in the last one, the middle corner is on the right side of the top corner, but the bend is still on the left side. Coincidentally, the center triangle is also equilateral, and the next one is a right-angled triangle, but those aspects are irrelevant. Let's take this triangle for example. It has 3 corner points, A, B and C, at some particular coordinates. It is comprised of 3 edges. Let's examine one of these edges more closely. Edge AC runs between y coordinate 0 and 11, and in that span it goes from x coordinate 7 to 12. How do we calculate what the x coordinate should be for some particular y coordinate along the line, such as 6? The answer is interpolation. The interpolation formula looks like this. You begin with a starting position. This is the x coordinate at the top of the line. Then you have a distance to cover. This is the difference between the end and start x coordinates. This distance you multiply by how far you have gone. In this case, the difference between your y coordinate and the top y coordinate of the line. You divide this product with the distance you are going to cover. This is the difference between the end and start y coordinate. You can use this generic formula for interpolating anything. For example, how much money you have earned in the middle of the month if you know your monthly salary. Now let's fill in the y coordinate 6 in the formula and see what the result is. 12 minus 7 is 5, 6 minus 0 is 6, and 11 minus 0 is 11. 5 times 6 is 30. 30 divided by 11 is 2.727... And plus 7, that means the x-coordinate when y equals 6 should be 9.727. Because pixels only exist at integer coordinates, you have to either truncate or round the number. We get either 9 or 10, depending which method we choose. If we repeat this process for all y-coordinates between 0 and 11, we get this line for the right edge. Then we repeat the process for the first line on the left side and the second line on the left side. We have 2 lines on the left side because the bend is on the left. Now you may be wondering, that second line on the left has gaps in it. Won't those gaps cause problems? Do we not need to solve also these intermediate coordinates somehow? The answer is no, we don't. We just draw horizontal lines between each pair of left edge and right edge. We go from the left x-coordinate to the right x-coordinate and plot all pixels in between. By doing so, we have succeeded plotting the entire triangle. However, if we have multiple triangles that share the same edge, some pixels are going to be drawn multiple times. To avoid that, we actually need to ignore the last pixel either on the left or right side and the last line either on the top or the bottom. I chose the right and the bottom because it is simpler to code it that way. The pixels I just removed belong to any possible polygon that is neighboring this polygon. Let's put this into code. We begin with a function that does triangle rasterization. This function takes the 3 edge points of some type. We don't care what the type is, just as long as the user also supplies a method for extracting the x and y coordinates for each of these edges. We collect the 3 edge points and sort them in descending vertical order, so that the first point is on the top, the second point in the middle and the last one at the bottom. If 2 points are on the same scanline, put the left side one first. We don't care about preserving the winding direction of the points here. It's totally fine if we change clockwise into counterclockwise or vice versa. Then we create 2 slopes. We will track the left edge of the triangle and the right edge of the triangle. One of these edges will run straight from the top to the bottom, and the other edge, where the bend is, will first run from the top to the middle and later from the middle to the bottom. A cross product will determine whether the bend is on the left side or the right side. In the main rasterization loop, we first process the section of the triangle that is from top to the bend in the middle, and then the section from the bend to the bottom. Both of these loops begin with calculating the slope of the edge. If the top edge is flat, then y0 will be equal to y1 and the first loop will not be run. If the bottom edge is flat, then y1 will be equal to y2 and the second loop will not be run. However, generally speaking, the compiler will generate more efficient code if the function invokes a lambda parameter in just one location. Therefore, I convert these 2 loops into one loop. And this is the core of the triangle rasterizer. We will not touch it again in this video. Now we just need to define the lambda functions. This draw polygon function will call the rasterizer I just defined with 3 lambda function parameters. The first one, getXy, defines how to get a coordinate pair from one of these points. In this case, the functor just returns the point itself. The second functor generates a slope, and the third one draws a horizontal stripe of pixels, i.e. a scanline between the left edge and the right edge. Now I'm going to pause for a moment. Remember this linear interpolation formula? Hold on, let me make it bigger. There we go. We have here an additive expression, inside which there is a multiplicative expression. You know that a times b is the same as b times a, and a times b divided by c is the same as a divided by c times b. Watch what happens when we switch places of these 2 expressions. We get this. Now what good is this operation for? The thing is, if the start and end coordinates are constants, we get 2 constants and 1 addition. The starting position is the starting x-coordinate, and the second group is the number that is added to the x-coordinate after every scanline. Let me show what I mean. Suppose we have a line that begins at 2030 and ends at 140. The starting and ending x-coordinates are therefore 20 and 100, and the starting and ending y-coordinates are 30 and 40. We are trying to solve x-coordinates, so the starting value is 20. By using the formula shown at the top of the screen, we can calculate the increment and we get 8 for the result. The x-coordinate at line 30 is 20. Now every time we move one scanline down, we add 8 to the previous result, and the results are shown in the bottom of the screen in red. So let's do that in program code now. We take the beginning x-coordinate and the difference between the begin and end divided by the number of lines. That's it. When we draw the scanline, we just sample the current x-coordinate on both sides, draw pixels between them using a for loop, and after that add the increment into the x-coordinate on both respective sides. And that's all. Now to demonstrate the program, let's add a main program. This main program will open a 2D window, create an array of several triangles, and then draw each of those triangles in a single color. Now which color should we assign each triangle? Things are more visually interesting if we give each triangle a different color. We should also make sure that the triangle splitting code works perfectly without gaps or overlaps. I added some extra colors and an if clause to deal with that situation. And this is the output. Now if there was a mistake somewhere, such as an off by 1 error, the screen might look like this. When you create your own Polygon rasterizer, I strongly recommend you make a test like this to catch this kind of errors. It helped me and it will help you. Now that we have proven that the code works, we can do some refactoring. I will take the slope code and create its own class from it. Later on, this will help avoid code duplication when we add more slopes. Now, so far our triangle corner points have been erased with 2 components, x and y coordinates. But we can just as easily add a few more components. Let's say a color, a red, green and blue component. Give every corner a different color. This makes our corners arrays that have 5 components, x and y coordinates and the red, green and blue values. In the draw polygon function, we change the slope data such that we now track 4 slopes on each side, the x coordinate and the red, green and blue values. We don't need to create a slope for the y coordinate, because that is handled by the rasterizer, which simply just goes through the triangle from top to bottom. After drawing each pixel, we advance all 4 slopes on both sides. This is the outcome. Something is wrong though. Look at this triangle for instance. Its top corner is ultramarine blue, the left side color is chocolate cosmos and the bottom corner is aquamarine blue. But why is the right side of the triangle also in a reddish shade? Shouldn't it be a completely smooth fade between the 2 blue shades? A closer examination of the entire picture reveals that all of the color shades are entirely horizontal in this picture. This is because I only did vertical interpolation in this program. We also need horizontal interpolation. I will create new slopes in the scanline function and set them to interpolate the props, that is the red, green and blue color, from the left side to the right side. These props are incremented after every pixel rather than after every scanline. And now it renders the intended way. All of the triangles are smoothly interpolated between their 3 corners. Now that the code has been proven to work, it is time to do some more refactoring. I don't want to change the draw polygon function every time I add or delete props, so I will make it generic. Let's make it templated so that it accepts any kind of points. We use std tuple size to determine how many props there are and change the loops accordingly. As a slight inconvenience, because we have to use std_get to access elements and it needs a compile time constant for the index, we have to change the for loop into a slightly different construction. This is a C++ thing rather than a texture mapping thing, but let me explain what this does. Below is a regular for loop in C++, and above is how you can transform it into a compile time loop. You only need this sort of stuff if the code inside your loop requires that the loop variable is a compile time constant. Let's go through this snippet in detail to understand what it does. First, this expression at the bottom creates a structure of a special type. It creates an std index sequence with template parameters that form an integer sequence that goes from 0 up to 1 less than the specified limit. At the top, this is a lambda function expression. It is an unnamed function, it doesn't have a name. It only exists until the next semicolon, after which it is gone and no longer exists. The bottom part calls this function. In other words, we are declaring a local function and immediately calling it. This section defines what kind of parameters the function takes. It has 2 parts. The first part defines template parameters, and the second part defines the actual variables that are passed as parameters. This means that the function can take as a parameter some index sequence, and the numbers that form the index sequence form a template parameter pack. The ... means a pack. It means that p is not just a single number, but it is a list of numbers under a single name. So this function takes some std index sequence as a parameter. This parameter is not given a name because we don't actually need to do anything with the object itself. We are only interested in the integer sequence that is used to define the object. And if size was 8, for example, the integer sequence will be 0, 1, 2, 3, 4, 5, 6, 7. This entire sequence is denoted by the pack called p. So now we are inside the function, and we have a pack of compile time constants called p. This comma ... part here means that the preceding expression will be expanded using the comma operator over all the values in the pack used in the expression. Because of the ... the compiler will treat your code as if you had written this instead. If you had a plus sign there, the compiler would expand the expression with a plus operator instead. So what does the comma here mean? It means essentially the same as a semicolon. It means that the expressions will be evaluated in a sequence, and the last value will be the return value of this parenthesis expression. You can use this kind of syntax also to generate function parameters. For example, if you put the ... inside a function call parameter list, the compiler will generate a function call with all the values from the pack. The expression you are expanding may contain any sort of details, and all of those details will be duplicated for every item in the pack. So back to the actual code now. You can see how I transformed the first loop into a compile time loop, but not the second one. This is because the second one does not require that p is a compile time constant. Finally, I used std_apply to call the plot function. You don't always need to use such complicated syntax in C++. The standard library contains many helpers to make your code simpler despite the underlying complexity. It is worth investing time to learn them. Now that we have changed the function into a more generic form, we can use tuples instead of arrays for the points. This change does not really serve any other purpose than to make the declaration simpler. The number of 5 is not particularly important information to the reader, so it is nice if we don't have to specify it explicitly. And that concludes the introduction. In the next episode we will move to texture mapping and also cover bilinear filtering, perspective projection and clip planes. If you liked what you saw and you would like others to see it too, remember to hit the like button, or the dislike button if you're so inclined. YouTube uses that feedback to decide whether to promote my content or not, so it is quite important for the growth of my channel. Have a nice day and see you soon again.